Okay, the first two questions are on problem 611. We've actually seen this before. We saw it when we studied forces. So there's two ways of understanding. Let's play the simulation and watch it. So you see. Okay, so what did we see? We saw both objects start at rest. They're tied together, so they have to move with the same velocity and the same acceleration and the same distance. And the simulation plots for us the velocity over time. And we can study this from force and acceleration point of view, or this time we'll study it from an energy point of view, and we'll do that in the second part of the problem, the energy analysis. The first part is simply taking measurements, and so your cursor will give you readings of the position, and so in this case you've been asked to place the cursor at the center of the objects, and so you want to do that very carefully in both cases and get the positions at the beginning and the end so you can find the delta x and the delta y. Notice that this is marked x from the previous time we did it, where we have an acceleration in the x direction. We want the acceleration of this to be in the x direction. This time we're ignoring this. We're treating this as y because the object is going to lose gravitational potential energy as what? As both objects gain kinetic energy. So that will be the energy analysis in the second part. So this is pretty straightforward. They both start at rest, and from an energy point of view, the energy, they're going to both gain kinetic energy, right? They'll both gain kinetic energy as they gain velocity, and because they're tied together, they have to have the same velocity. And so where's that kinetic energy coming from? It's coming from the change in gravitational potential. This is the only source of energy. This one doesn't change gravitational potential energy. And so this goes from a kinetic energy of 0 to 1/2 mv final squared. The hanging block starts with a kinetic energy of 0, and the loss, the energy that's lost to supply that kinetic energy, is the energy of the falling mass. So in terms of conservation of energy, we have work by non-conservative forces equals the change in kinetic energy plus the change in potential energy. But since it's frictionless, this term is 0. And so the change in kinetic energy equals negative the change in potential energy. And the change in potential energy only comes from the hanging mass. That's going to be mgh, which you need to measure, the h. And the kinetic energy is going to be the change in kinetic energy of the two objects. They both start at rest, so it's going to be Ke final for the cart plus Ke final for the block or the hanging mass. And the masses are given, and the velocity you can get off the graph. And that way, so the total energy, and this is negative, right? Because the delta H is negative. So the delta H is negative. This becomes a positive quantity, and it's split between these two things. Calculated from the velocities. Okay, question 3, activity 3, based on problem 612. So as usual, read through the description of the situation carefully and then run it. And then run it through your mind. Think about it before you start answering questions. Just think about what you see, what you're observing, what you're understanding in preparation for answering the question. So let's run it. Starts from rest, goes past the middle, goes to the far side and stops. Okay, so the spring was compressed. It decompressed and then got to the middle, and because it was moving, continued moving and stretched the spring out. So what we're seeing is half an oscillation. The middle is somewhere here. Say it started here and it's going to oscillate. You know, we just stopped the video, right? But since it started at the turnaround point and it ended at the turnaround point, the velocity at the beginning and the end should be 0. But at that point, the force is max. So what we want to remember is the spring force depends on the amount that it's stretched or compressed, right? So where the velocity is 0, the force is maximum. So the acceleration's maximum. And where the force is 0 in the middle, right, where the spring force is 0, it's actually going to be instantaneously 0. That's the relaxed position. If we just let it go to its relaxed position, right, it would be there. But you compress it here and then it oscillates back and forth. So in terms of energy, over here it has spring potential energy. In the middle, the spring is unstretched, so it's all kinetic energy, and then it goes back to spring potential. And because from the description you can ignore friction, there's no work done by non-conservative forces. So the work by non-conservative forces is 0. I use PE, but don't forget there's U, because that's actually what we'll use next semester. So we have K and U spring. It doesn't go up and down, so there's no UG. And so the only two energies, spring potential energy and kinetic energy. And we just described how it goes. And first we need to identify the graph. Okay, so first of all, we can reject graph 4 because the spring force isn't constant and then in the middle instantaneously switches to a negative constant value. No, it changes gradually. But does it change in a curved way? This is like an exponential, or is it linear? It's linear, right? This is a linear equation. There's a constant. The x varies according to f according to a constant. So it's got to either be graph 2 or graph 3. But the spring force in the beginning is pointing this way. So it should start positive. Linearly go to 0, where x equals 0. And then go to its maximum negative value, because when it's at this end, at the far end, the spring force is pulling back and it's negative. And since this is displacement, right, the area under the curve, this is interesting from a calculus point of view, the integral of f dot dr or dx, right, that integral where f is varying is the work. And so the area under the curve, so notice the spring does a positive work on the ball, turning it into kinetic energy, and then the kinetic energy does, the spring does a negative work on the ball. And so the net work from one end to the other is 0. And by work, right, I'm not talking about work by non-conservative forces. I'm talking about the work done by the spring. Okay, so graph 3 is the graph. And since we know the force and the displacement, we can get K. Right, using Hooke's law. And since we know K, we can get the spring potential energy, 1/2 kx squared, at the maximum. And since the energy at either end is all spring and no kinetic in the middle, so if we say U spring max equals 1/2 kx squared max, that's the maximum, either positive or negative, right? That's going to be equal to the 1/2 m Vmax. And where is Vmax? Vmax is at the center when the spring potential is 0 squared, right? So those are all the equations you need. I'll leave you to solve the numbers and do the measurements. Okay. Okay, next, 613. Let's play it and watch what happens. There's a hand on the cart. Spring is compressed. We start it. You see, it's telling us the velocity. You can see it's moving at a constant speed. That's not what happened in the last one, right? And why? Because there's a hand pushing. So the hand's exerting a force that's causing the thing to maintain a constant speed. Okay, so the description tells you mostly, but can you puzzle out what's going on? What's going on if the speed is constant? Then if we go back to the beginning, see, the force of the hand on the cart has to be pushing against the spring, right? Because if the speed is constant, the sum of the forces have to be 0. Right, there's no acceleration. And so that means that the spring force must be equal and opposite to the hand force at all times. And remember what we learned in the last one, that the spring force varies, right? It's going to be maximum here. Let's just say this is where it goes to. That's the middle. So the spring force is maximum at the ends, and so the hand force has to vary. That's not obvious at first, but it actually tells us that in the description. By applying a varying force, you allow the spring to relax and then cause it to stretch while maintaining an equilibrium during the entire process. Okay, this is a little tricky when you first see it. You may be fooled by it. Okay, watch the vector arrow for the force of the hand as we run it. Here we go. So you see the arrow shrinking, because the spring force is getting less and the hand is matching the spring force, and now the spring is being stretched, so the velocity should be slowing down, so the force of the hand has to get bigger and bigger to keep the velocity constant as the hand matches the spring force, which is pulling now at this end in the other direction, right? It's equal and opposite in this direction. And so now the energy analysis. Work by non-conservative forces equals delta K plus delta U. It's less writing, so I'll use the U instead of the PE. And the kinetic energy is constant, so there is kinetic energy, but it doesn't change, right? The change in kinetic energy is 0. And so the work by the hand, the non-conservative force, matches the change in spring potential energy. And so during the first half of the cycle, the work is negative, taking the energy lost by the spring, and in the second half it's positive, putting the energy back into the spring while maintaining a constant kinetic energy. And so over the whole cycle, the work is always matching the change in gravitational potential energy, but opposite in sign. Okay, number 5, 6.14. Let's run it and watch. Okay, so it's familiar to us now. Here there's no hand. It's just doing its natural thing, oscillating back and forth between two extremes, and keeps going. So this one, the video just keeps running. So you see in the description, you have the mass of the cart. It's on an air track, so that means no friction. And you want the spring constant. And so this is an energy problem. Don't make this mistake. Don't try and get the spring constant using Hooke's law. Why not? Because you don't know the force. What we do know is the velocity that's given to us. And so if we use conservation of energy, work NC equals the change in kinetic plus the change in spring potential, no gravitational potential here. And since it's an air track, this is 0. And so the energy is simply, as we've seen in a lot of the others, except the one with the hand, kinetic energy. Well, what you start with is you start with potential energy. I'll use the U, could be PE, right? U equals 1/2 kx squared, and we can measure the x. So this is how we get the k, but we have to know this. And how do we know this? Well, we know that this is going to be opposite or negative the kinetic energy. And so at this position, all of the energy is in the spring. And so where x is max, that's the total energy of the system, right? At this point, the starting point and the other end point, there's no kinetic energy. All the energy is spring. The energy will be constant. If we go to the middle, the spring energy will be 0, and the kinetic energy, all of the energy will be in kinetic energy. And so we can calculate the energy of the system by calculating the energy at the point where there is no potential energy, and that's 1/2 m v max, right, squared. And how do you get the v max? Well, the simulation gives you that. And you have these stepping buttons that allow you to zero in on what the maximum velocity is. So I hope that's all clear. I'll say it one more time. Get the energy at the end, where it's all spring potential energy, by finding the energy, the kinetic energy, in the middle, where it's all kinetic energy. And since the energy of the system is constant, right, because there's no work, it's frictionless, the energy, so in the middle it's all kinetic, at the end it's all potential. Every other place it's a mixture. But if you find the total energy of the system by finding the kinetic energy in the middle, that will be the potential energy at either end, and you can measure what the position is at either end, and thus you can calculate K is going to be 2 times the energy of the system divided by the x squared, and the total energy of the system, and the energy at the end, right, is 2k max, where it's in the middle, over x squared. All right, good luck. Okay, last exercise, number 6, problem 7.8. Dropping a ball. This is a real ball. Under normal circumstances, we do this exact same thing in laboratory and take measurements. So watch what happens when I play it. The ball falls, bounces back, and like a real ball would, it doesn't go as high as it did the first time, and then it stops the animation before it rebounds again. So this is pretty easy in that the time is given and the position of the ball is given, so you don't have to actually do those measurements. And so what we have is we're thinking of the ball as a spring, and because it doesn't rebound to the same height, there is a loss of energy. And so the work, in this case, the work by non-conservative forces is not zero. And we have kinetic energy, gravitational potential, and spring potential all there. So when we start, what do we have in the beginning? In the beginning, all gravitational potential, right? There's no kinetic, there's no spring, and then we let go. Whoops. We let go, it falls. I'm going to pause it and step it. So it's losing potential, it's gaining kinetic, and at this point, the work term is zero because we can ignore air resistance. And then finally it hits the ground and it stops. So all the gravitational potential changed to spring potential. And all the gravitational potential changed to kinetic the instant before it hit. And then in really a very short time, all that kinetic energy goes away because the ball instantaneously stops at the bottom. And so it's all stored in the ball like the ball is a compressed spring. And then it bounces back, but it's not going to go as high. So the kinetic energy, so notice we start out with, let me write this down. At the top we have gravitational potential energy. That changes to kinetic energy just before it touches the ground. In a very short time, all that kinetic energy goes into compressing the ball as a spring potential energy, and then the ball bounces back, giving us kinetic energy, but it's going to be less kinetic energy than when it went in. Why? Because the kinetic energy then goes back into gravitational potential energy, and the only time there's work is during the compression of the ball, right? Because the ball is not a perfect spring. There is some non-conservative force. The ball is going to get a little bit heated up from the bounce. If we could measure its temperature, we'd see that it was slightly hotter after the bounce than before the bounce. So there's a lot of energy transitions here, but the work by non-conservative forces all happens during the time of the compression and decompression of the ball. And so if you calculate the original energy when we started at the top, that's the starting energy, and then when it gets back here, all of the energy is potential energy. And so that amount of energy difference is the loss of energy. And if you divide that into the starting energy and multiply by 100%, you'll get a percent. But you need to be very careful. If you get partial credit, it means you have a rounding error. So when you report your answers, say for the original gravitational potential energy, you're going to have a number to 3 digits, but there's more than 3 digits, and so beware the rounding error, especially if your percent energy loss only gives you partial credit. And last but not least, the times at which you can find each of the laboratory exercises in the video if you just want to single out one and watch the one without watching the rest or having to fumble around to find it. There it is, the table of contents at the end.